Hello, class. This is a cartoon that I remember seeing when I was taking, I think, a graduate level course in biothermodynamics. And the student says, "Beat me, hurt me, teach me thermo." That's what we're doing. Okay, consider the following two reactions. One is a phase change, and the other is a chemical reaction. The phase change reaction, we have water, solid water, that's ice, melting to liquid water. And we have at the right something called an enthalpy change, which we'll talk a little bit more about in a second. And that enthalpy change is 446 kilojoules per mole. And then the second example is the chemical reaction of water being broken into its elemental components, hydrogen gas and half an oxygen molecule. And we also have an enthalpy change, a delta H, of 242 kilojoules per mole. So what are these thermodynamic values, these enthalpy changes? Well, because up to this point we've talked about an energy change. Well, an enthalpy change is very similar to an energy change, and for all practical purposes in this class you can assume that they're the same. But to be technical, an enthalpy change is equal to an energy change, which is more correctly called an internal energy change, a delta E, plus a pressure times delta V, a volume change term. Now, the reason we can usually equate enthalpy changes with energy changes is that for most reactions, the pressure times volume change term is very, very small. And secondly, we are usually working at constant pressures of like 1 atmosphere. That is, most of the chemistry that happens around you happens at 1 atmosphere, most that you know about. So for all practical purposes, when we talk about an enthalpy change, it's essentially the same thing as an energy change. And so the same definitions that we use for energy change also apply for enthalpy changes. That is, if we have a positive enthalpy change, delta H, this corresponds to an endothermic reaction, one in which thermal energy would be transferred from the surrounding into the system. If we have a negative enthalpy change, this corresponds to an exothermic reaction in which thermal energy is given off from the system into the surroundings. And we see that in our two examples above, both of these are endothermic reactions. That means if we had them in our system, in our test tube, and those reactions were to take place, we would feel thermal energy being transferred from the surroundings into the system. Or in other words, it would take an input of thermal energy to even make these reactions go. And we will see in the next slide or so how we interpret these energy or enthalpy changes in terms of energy diagrams. And we'll see that when something goes up, that when the change is going upwards, that means there has to be an input of thermal energy to make the reaction go. That's an endothermic reaction. On the other hand, when a reaction goes down in energy or enthalpy, that is an exothermic reaction, and that reaction usually wants to go by itself, even being spontaneous. That is, it wants to go downhill. So for the two reactions shown, these are endothermic reactions. Now, whether or not a reaction wants to go will depend upon some other considerations that we'll get to later, which means the second law of thermodynamics. That's when we have to take even more punishment in learning our thermodynamics. But for right now, we just wanted to point out that we will be discussing enthalpy changes for the most part for the rest of this chapter. Another reason for talking about enthalpy changes is that in the next video lesson, we'll talk about calorimetry. And there are really two types of calorimetry. One is what we call coffee cup calorimetry or constant pressure calorimetry, and the other which we call constant volume calorimetry. Well, the constant pressure calorimetry experiments are easier to conduct, and those are the ones where the actual measurement that we make is of the delta H, the enthalpy change, whereas a little bit more difficult constant volume calorimetry changes are the ones that give us delta E's. But for all practical purposes in general chemistry, delta H and delta E can be considered essentially the same thing. What we want to talk about in this video lecture is the concept of Hess's law and also how to operate or how to handle delta H or delta E values. So we had a chemical reaction. Water water vapor, water in a gas phase, being split apart into a hydrogen gas molecule and a half an oxygen molecule. And we said that that is an endothermic process. The delta H is 242 kilojoules per mole. A couple of things. What if we wanted to invert the reaction? Having the reaction go in the opposite direction, essentially saying hydrogen gas plus oxygen, half an oxygen going to water vapor. If we inverted the direction of this reaction, the enthalpy change would be equal and opposite in sign. It would be minus 242 kilojoules per mole. It would be exothermic, going in the opposite direction, you see? If it's going as written, it's endothermic, 242 plus 242. If it were written in the opposite direction, it would be exothermic, minus 242 kilojoules per mole. Another thing to point out is that these enthalpy changes are per mole of the reaction as written. And so I ask the question, if you have 1 mole of water vapor and this reaction occurs, it would require an input of 242 kilojoules of energy from the outside somehow to make it happen. What if you had 2 moles of water and you wanted to have the reaction with 2 moles of water converting to hydrogen gas and oxygen? Well, logically, this would take twice as much thermal energy. It would be 484 kilojoules of thermal energy required to have 2 moles of water molecules undergo this reaction. And in general, if you see this equation, the amount of thermal energy, Q, is equal to delta H times N, or in other words, delta H is equal to Q divided by N. It's the thermal energy, either output or the thermal energy required, divided by the number of moles of the reaction. Okay, we usually say per 1 mole, but if we had more than 1 mole, point is we'd have to multiply up. Let's continue on and discuss the way we operate with enthalpy changes. And really what we're talking about is Hess's law in what are called functions of state, because the enthalpy change is a function of state. I'll explain that a little bit more in a second. So in the previous slide, we had the reaction written water going to hydrogen gas and a half an oxygen molecule. Here, I'm in fact writing it in reverse and showing again that if we were to write this reaction in reverse, it would be exothermic, minus 242 kilojoules per mole. And over to the right, I show an energy or enthalpy diagram showing an energy level for hydrogen gas plus half an oxygen molecule, showing that if hydrogen gas and oxygen react together to form water, they will go downhill enthalpy-wise or energy-wise to a lower level for water vapor. How much lower? 242 kilojoules lower than the value for the starting reactants. Now I also show a second reaction. Hydrogen gas plus oxygen going to water, but this time in the liquid phase. And the enthalpy change for this reaction is slightly larger in magnitude, minus 286 kilojoules per mole. And I show that also in the diagram to the right, where if you start at the same point with hydrogen gas and a half an oxygen molecule, and in this time, instead of reacting to water vapor, you go to water liquid, you would actually go to a lower enthalpy level, minus 286. And continuing in our discussion of how to operate with these enthalpy diagrams and how to handle delta H's, I'm switching back again and showing you the reaction written in the first way, where it's endothermic. Water vapor being split apart to hydrogen gas and half an oxygen molecule, plus 242. And at the right, you see the enthalpy diagram where you have water vapor, and then to split it apart to hydrogen gas and half an oxygen, you're going uphill. How far? 242 kilojoules. And likewise, I have the second reaction, water in the liquid phase, which starts down a little bit lower, and it also breaking apart into hydrogen gas and a half an oxygen molecule. There, the step is 286 kilojoules. So the point is that we can either go up or down, depending on how we define our reactions. What is the reactant? What is the product? To determine whether or not it's an endothermic or exothermic reaction. But also, did you notice I have water vapor and liquid water in this diagram to the right? Liquid water is like a cup of water, and water vapor is water vapor. That's a phase transition. What would be the enthalpy change in going from liquid water to water vapor? And can I not obtain that value from the information provided? The answer, of course, is yes, because if you think in terms of adding vectors, then that should be the arrow shown, and you can probably figure out what the magnitude is. It should be 44 kilojoules. That should be 44 kilojoules per mole. And in fact, this is one of these applications of what is called Hess's law. That is, when we have a set of reactions that are somehow linked together, we can determine the value, if there is an unknown enthalpy change for a reaction, by adding and subtracting the other values. Again, it's much like just adding vectors. So let's show another application of what is called Hess's law. Let's say, well, this one looks kind of messy, but I assure you that it's not as bad as it looks. Do you trust me? Beat me, hurt me, teach me thermo, right? Let's say that you're given in a problem the enthalpy changes for a set of reactions. Can you then calculate the enthalpy change for an unknown reaction? Okay, so the given reactions are 1, 2, 3 on the left, and the unknown reaction is near the bottom of the slide. That is, the given reactions are, first, the reaction of carbon in a solid phase plus oxygen gas to form carbon dioxide. And I give you the delta H for that. And notice that it's a fine exothermic delta H, minus 393.5 kilojoules. Thermal energy given off from the system to the surroundings. It feels hot because thermal energy is given off to the surroundings. And that's not surprising because that's essentially the burning of coal. The second reaction, carbon monoxide plus oxygen reacting to form carbon dioxide gas. That also turns out to be an exothermic reaction, minus 566 kilojoules. The third reaction, hydrogen gas plus oxygen gas to form water vapor. Well, this is the same reaction that I had before, except I'm now doubling it because I'm doubling the stoichiometries of the reaction. If you recall, previously I had one hydrogen plus half an oxygen going to a water, and here I'm doubling things, and so if you notice this value, it's twice the value that I had before. Okay, so the concept is the magnitude of the enthalpy change will depend upon the way the reaction is written and also the stoichiometry, whether or not we've doubled the stoichiometry or not. But I digress. So here are our three given reactions where the information, the enthalpy changes are given for three reactions. And the question is, can you use these delta H's to calculate the enthalpy change for an unknown reaction? The unknown reaction is carbon solid, reacting with water vapor to form carbon monoxide, gas phase, plus hydrogen gas. What is the delta H for this reaction? Oh, how do I get this? Well, I'll tell you the answer and then we'll back up and show you how. This unknown reaction is actually the sum of the first reaction minus 1/2 the second reaction and minus 1/2 the third reaction. And the enthalpy changes are then additive in that way. That is a property of enthalpy changes, a consequence of enthalpy changes being what are called functions of state, which we will explain in the next slide. So, backing up, the unknown reaction is reaction 1 minus 1/2 reaction 2 minus 1/2 of reaction 3, and so we can calculate the enthalpy change in the same way. It's the enthalpy change for reaction 1 minus 1/2 the enthalpy change for reaction 2 and minus 1/2 the enthalpy change for reaction 3. We put all that into our calculator and we can calculate the enthalpy change for this unknown reaction, and it turns out to be minus 918.3 kilojoules, a very healthy exothermic reaction. It would really feel hot if we're trying to hold the system as a test tube in our hand. Okay, but the question is, how did I determine, by looking at these three, that it's the first reaction minus 1/2 of the second minus 1/2 of the third? That's the scary part, right? Well, not so bad. Actually, if you look at this, here's the way you handle this. Look at the unknown reaction. And as I always say, start with the first thing you see. Don't make it complicated. Start with the first thing you see. The first thing I see is carbon. And I look above. Where does carbon appear in the three reactions above? It only appears in the first reaction. And notice that it appears on the reactant side of the first reaction. That's where I want it to be in my unknown reaction. I want it to be on the reactant side. So I don't necessarily see the other parts of reaction 1, the oxygen, the CO2, but just trust me, they're going to cancel out. So the first thing I see is carbon in my unknown reaction, and if I look above, I see carbon on the reactant side for reaction 1. So I begin by thinking, I bet reaction 1 has to go in a forward direction. Then I look at the second thing I see in my unknown reaction, and it's water vapor. And I look at the 3, and the only place I see water vapor is in reaction 3, and it's on the product side instead of the reactant side. And I see 2 water vapors, and I only need 1 in my unknown reaction. You see, it's starting to make sense now, right? So reaction 3 has to be written in reverse. That's where the minus 1/2 of reaction 3 comes in. It has to be in reverse, minus, and I have to cut the stoichiometry in half because in my unknown reaction, I only need 1 water vapor molecule, and in reaction 3, I have 2. So minus 1/2 of reaction 3. Now keep trusting. Okay, and then I look at the next thing I see in my unknown reaction, and it's carbon monoxide. Okay, now I look to the 3 unknown reactions, and the only place I see carbon monoxide is in reaction 2. Oh, yeah, that's good, but here again, I want carbon monoxide on the product side, but in reaction 2, it's on the reactant side. And to boot, the reaction 2 has 2 carbon monoxides. Okay, but I'm feeling a little better. I think I can handle this because I need to say minus reaction 2, but also minus 1/2 of reaction 2 because I have to cut the stoichiometries in half. Okay, the fourth thing I see is hydrogen gas in my unknown reaction, and the only place it occurs is in reaction 3, and I think it's going to work out because I've already included reaction 3, having it go in reverse and cutting the stoichiometries. I bet that's going to fall in place, and it will. And if you write it all out in that manner, reaction 1, just write them all out as a string. Reaction 1, then reverse the sign of reaction 2 and cut the stoichiometries in half. And then reverse the sign or reverse the direction of reaction 3 and cut the stoichiometries in half. And then cancel everything out that needs to be canceled out. You know what you'll wind up with? The unknown reaction. It works. Now you have to have a little faith in some of this. You got faith? That is, if you're going to be asked a question like this, it's going to work out. Just keep going forward and follow that logic. Point is, we can use Hess's law if we have a set of known reactions to calculate the delta H for an unknown reaction. Now, of course, we have to be given the right set of known reactions, but again, you have to have some faith. After all, you're taking enough punishment, right? All right, now we said that enthalpies and enthalpy changes are functions of state. Now, first of all, what's enthalpy and enthalpy change? When we have an enthalpy diagram and we draw a level here or here, these in principle have numerical values, but we really don't know what they are, but we can determine the value of a change between enthalpy levels. So it's the enthalpy change that we deal with most of the time. And we say they're functions of state. Now, what do we mean when we say they're functions of state? Does that mean it's going to be a formal dinner in the White House? Do we have to wear a tuxedo? Well, not really. It means that they are additive quantities, and especially they're additive quantities for connected reactions. And when we say state, we mean like physical state, like is it a solid, liquid, or gas under standard conditions. So standard state conditions refer to 25 degrees Celsius, which is 298 Kelvin, 1 atmospheric pressure, and if we're talking about solutes dissolved in aqueous solution, 1 molar solutions. So these are standard conditions. So what do I mean by this? If I say water in the standard condition, you say liquid water. If I say sodium, you say in the solid metal state. Okay, so that's what we mean when we say enthalpy changes are functions of state. Now the bottom half of this slide is pretty important. It talks about molar heats of formation of molecules. Ooh, what does that mean? All right, look at the 3 reactions that I've shown and look at them for a second and see what you think. Each of these reactions, and there are just dozens and dozens of reactions of this sort, each of these reactions has only the elements on the reactant side forming some product molecule. You notice that? For example, the first one says carbon in its standard state, solid. Oxygen in its standard state, liquid. Going to carbon dioxide in its standard state, gaseous form. Okay? And then I give the delta H of formation for carbon dioxide. Forming carbon dioxide by reacting together the elements under standard state conditions. See? And the delta H for this reaction, this is called a formation reaction under standard conditions. So we use the symbol delta H, superscript 0, which means standard state conditions, subscript F, which means formation. And that value is minus 393.5 kilojoules per mole. Now somebody has determined this number and they put it in a table for us. Okay, let's think them. Second reaction. Hydrogen gas plus 1/2 an oxygen molecule going to water vapor. Hydrogen in its standard state, gaseous form. Oxygen in its standard state, gaseous form, going to water. The enthalpy change for formation of water vapor is minus 241.8. Now earlier we said minus 242. We were rounding. Minus 242 kilojoules per mole. The third reaction, magnesium, solid state, carbon in its solid state, plus oxygen in its gaseous state, forming magnesium carbonate. Delta H of formation under these standard conditions, minus 1,095.8 kilojoules per mole. Okay, so the point is that there are scads of these reactions in which we can take any of the elements, react them together to form product molecules. And if the value of the delta H of formation under standard conditions, if those have been determined, we can put them in tables. And once we have them in tables, we can use them. How can we use them? We can use enthalpies of formation to estimate the enthalpy change for unknown reactions. Again, estimating enthalpy changes for unknown reactions. For example, let's say that we have calcium carbonate going to calcium oxide and carbon dioxide gas. The enthalpy change for this reaction, that is, let's say we don't know this enthalpy change and we want to calculate it. All right, we would calculate that as the delta H of formation of the first product molecule, calcium oxide, plus the delta H of formation of the second product molecule, carbon dioxide, minus the delta H of formation of the reactant molecule, calcium carbonate. Notice the minus, because that means we're opposite of forming calcium carbonate. Calcium carbonate is going away. It's opposite of forming. Okay, back up and say that again. The delta H of the reaction is the delta H of formation of the first product plus the delta H of formation of the second product minus the delta H of formation of any of the reactants. And of course, if we had stoichiometries of 2 or 3 in front of these, we'd have to be multiplying the delta H of formation by that stoichiometry. But in this particular case, it's a 1 goes to 1 plus 1, so we don't have to multiply by anything. But let's say that the delta H of formation of calcium oxide, carbon dioxide gas, calcium carbonate are all known. They're in a table somewhere, and we can look them up, and here are the values. I'll go ahead and share that these are the correct values. If I add these together, I get 178 kilojoules per mole as the enthalpy change for this unknown reaction. Okay, turns out to be an endothermic reaction. That means, actually in this case, that calcium carbonate, which is common chalk, for it to undergo a reaction to form calcium oxide and carbon dioxide gas, I would have to add thermal energy. I'd have to heat it up to make that reaction go. Now, that probably makes some sense to you because you don't see calcium carbonate reacting by itself, and you can only imagine to make this reaction go, you would have to add some thermal energy, right? Okay, so these delta H's of formation, I know what you're thinking, and you're thinking, show me a table so I can really get into this and do these calculations. Well, tables are found in your book. Here's a shortened version of this table. But in general, if we have a table of delta H's of formation, we can estimate for any unknown reaction the delta H of the reaction by summing up the delta H's of formation of the products, multiplying by any stoichiometries that exist in the balanced reaction, and then subtract the delta H of formation of the reactants Again, multiplying by stoichiometries if we need to. And I show you just an abbreviated example of such a table. Okay, we've covered a lot about Hess's law. In the next video lesson, we'll get into actual measurements of enthalpy changes using calorimetry. Fun to come.